In the early days of computer networks, we used hubs to connect our good old computers. A hub is nothing more than a physical repeater. When it receives an electrical signal on one of these interfaces, it will repeat it by sending it to all its interfaces except the one that received this signal. There is no intelligence in a hub, and it only works on the physical layer of the OSI model, the layer 1. Because interfaces share the same physical support, computers operate in semi-duplexes, and there may be collisions. To avoid these collisions, it is possible to use the CCNA CD protocol. The more computers there are in this type of network, the more likely there are to be collisions. In this topology, we have 4 PCs and a hub in the middle. If one of our computers sends data, the hub will simply repeat the electrical signal at all other ports, which means that everyone will receive that data, whether they need it or not. The network operates in semi-duplexes, which means that we can have collisions. Because collisions can spread anywhere on PCs in the same hub, we call this a single collision domain. As the network grew, there were more collisions, which had the impact of reducing business performance. Let's take another example. If you look at this topology, where do you think we're going to encounter collisions? As there are only hubs, collisions can happen everywhere. So this is a big collision area. These numerous collisions caused a huge drop in bandwidth at the time. So we had to find a smarter device than the hub. And that's how the bridge was born. The bridge has intelligence, and it works in layer 2 of the OSI model, the data link layer. The bridge is capable of deciding where to send Ethernet frames, looking at MAC addresses, transferring Ethernet frames to specific ports, filtering Ethernet frames, that is to say, remove those that are useless, flooding the Ethernet frames, that is to say, send them everywhere like a broadcast. On the other hand, a bridge has only a few ports, and they're very slow. Let's keep the previous image and add an identical topology, except that we replace the middle hub with a bridge. As the bridge has intelligence, it transmits Ethernet frames only if they are needed. So we have on this topology 2 areas of collision. If the PC at the top left sends an Ethernet frame to the PC, the bridge will receive this Ethernet frame on its left interface, but will not transmit it to the other PCs to the right. Let's go back to our time, because the hub and bridge are ancient history. Nowadays, we hardly use them anymore, because the switch has arrived. The switch has several ports. They may have different speeds per port, such as fast Ethernet or gigabit Ethernet ports. They have a large buffer. And they have 3 different switching modes. There are several types of switches, which use different methods to transmit frames. The standard model switches packages to deferred mode, which is called store and forward mode. It buffers the frames and analyzes them for possible errors before sending them. Switches also use a more direct mode. In this mode, the switch simply reads the destination address and transmits the information without analyzing it. And the third mode represents a compromise between the 2 previous methods. That is, they add a simplified error processing on the switching frame. Nowadays, most switches use the store and forward mode. Now, let's see how the switch works. On this topology, we have 3 PCs with a switch in the middle. The switch manages an MAC address table as it learns them. How many areas of collision do you think there are? Well, as we operate in full duplex, we can't have collisions in a dial-up network like this. Each interface on a switch is seen as a separate collision domain. This means that in this topology, there are 3 areas of collisions. One wonders, why are there areas of collisions when it is supposed not to have collisions? when it is supposed not to have a collision? Well, that's because it's quite possible to plug in a hub on one of the switch ports, and in this case, there will be collisions. To return to the operation of the switch, since we operate in full duplex, and we can no longer have collisions, the protocol CCNA-CD that we have already talked about is disabled. PCA will send data to PCB. It will therefore create an Ethernet frame that will contain the MAC address of the PCA in the source field and the MAC address of PCB in the destination field. The switch builds and manages an MAC address table, which it learns only based on MAC source addresses. Each Ethernet frame it receives, it will learn the MAC address of the source field of the frame, and it will make a relationship with the port number where it is. For example, the switch has just learned that the MAC address of PCA is linked to the fast Ethernet 01 interface. It will therefore add this information to its MAC address table. As you can see, our switch currently has no information on the location of PCB. To find out which port the PCB is on, it will flood an Ethernet frame. That is, it sends a frame to all these ports except the one where the demand comes from. PCB and PCC will therefore receive this Ethernet frame. Upon receipt of this frame, PCB sees its own MAC address in the destination field. So it deduces that this frame is intended for it. As for PCC, as it is not concerned, it will remove this frame. The PCB will therefore respond to the PCA, building a new Ethernet frame and sending it to the switch. It is at the reception of this one that the switch will learn the MAC address of PCB. The next time PCA wants to talk to PCB, the switch will switch the package directly instead of flooding the frame on all these ports in search of the destination MAC address. And that way, the PCC will no longer receive frames that are not intended for it. Let's see what the MAC table address as a switch really looks like. If we connect on the switch and launch the Show MAC Address Table Dynamic command, we will see all of the MAC addresses that the switch has learned. Here we see that it has learned the MAC address of PCA, B, and C. By default, there is no limit to the number of MAC addresses associated, and so all MAC addresses are allowed. For safety, it is possible to change this behavior with the function of port security.